Hi friends, today we discuss about decision trees and also we implement the decision tree model in Jupyter Notebook. As we know, decision trees are supervised learning models and they are very fast at runtime in terms of prediction, and also these are mostly used for classification, and these form the backbone of most of the best performing models in the industry like XGBoost, light gradient boost algorithms. Decision trees are highly interpretable. We can easily identify how actually a decision is made. Decision tree is made with a primary attribute. From there it will make its child nodes flow, but how actually that attribute is chosen. This selection of an attribute is based on the node impurity. So how actually this impurity is calculated, we will look here. There are three measures of node impurity: Gini index and information gain and gain ratio. By using these impurity measure, we choose our parent node. First of all, we discuss about Gini index. In Gini index, we'll first find the impurity of the node. C, based on this formula, where C represents the number of classes for classification. If we make a binary classification, C will be 2, and this P will be the probability distribution function of the class in the node. In a node, they will be further categorized. So from the categories, we find the class distribution. We'll see once an example from that will make us very clear. Now we look into this data of a car. A car of the different models. It has a different attributes like engine, AC turbo, weight, and fuel economy. Based on those attributes, we have to decide whether the car goes fast or not. We'll work on this to find the Gini impurity. It is a binary classification problem. So when you are building a decision tree, how do we choose this attribute based on the impurity measure? So we'll see how we'll measure the impurity measure. First of all, see, if we take the engine attribute, we have total 15 records. For each engine, further it is categorized into small, medium, large. So once we look here, when the engine is small, then it's classified the car is not going fast 5 times, and car goes fast, yes, 1 time. Similarly, for when engine is large, there are twice there is classified it as the car is not going fast. When the car is medium engine, 3 or 5 times is classified as not going fast, and 2 or 5 times it is classified as car is going fast. From these attributes we find this Gini impurity. For each value we find the impurity. So there are three impurity values. So we have to group them into single value. How can we do that? We can do that by using weighted average method. So how we'll give the weights? Since engine has 3 categories, and all these 3 categories, this category has 6, and this category has 5, and this category has 4. So 6 out of 15 times multiplied with this impurity. This is how the weight is calculated. So for engine attribute, the overall Gini split value is 0.40. This is what the value for one attribute. Similarly, there is other attribute SCR turbo. When car has turbo, what is Gini impurity? When car do not have turbo, 11 times, what is its Gini value? Since it has two values, again we use weighted average method to find this overall Gini impurity measure. So we got as 0.42. Similarly, for other attributes, weight and fuel economy, the final Gini value we obtained as, and similarly for other values we got. So we choose with the attribute with the lowest Gini value as our parent root node. So we will choose fuel economy in our decision tree as our first column to make our further decisions. This is how. Now we will discuss about second impurity measure, information gain. So first of all, to find the information gain, we require the entropy of the each attribute. So we'll find Shannon's entropy to measure the node impurity. What is entropy? Entropy is nothing but measure of randomness. Randomness tells us the degree of disorder in the system. So higher the entropy, we'll get more amount of disorderliness is present, so lower is the information we will get. This is the entropy formula. It is there. P is the probability of the class within the node. C describes the number of classes. Since our binary classification, C will be 2. Probability, this is our probability of the class within the node for that category. So information gain, we'll find it is amount of information present in any random variable. So how can we find the calculated information gain? So information gains tells us how much amount of entropy we have removed so far. It will give, so higher the information gain, the attribute with highest information gain will be chosen as our first parent attribute for to develop our further child attributes. This is how we will develop the gain information. So similarly, again we take the same table data of the car, which has model, engine and AC turbo, weight, fuel economy, and whether the car goes fast. Based on these attributes we have to decide. So when we are ready to build the decision tree, first we have to start from one attribute. So how we start, which attribute we'll choose to make our final decision depend by measuring the information gain. So we are removing those columns with unique values. So model column I have removed. Now this is our target variable. The target variable, it is classified. This is how it is classified. For this I'll find this entropy at the first split. What is this entropy? This is how I find the entropy, and I'll got this is the value I got. Similarly for other attribute, these are the these are the attributes. 4 cars has AC turbo and 11 cars do not have AC turbo. When 4 cars have AC turbo, out of the 4, 2 cases the car do not go fast and 2 cases the car goes fast. Similarly, when 11 cars do not have AC turbos, when they do not have AC turbos, so 3 times the car is classified as fast going car. We found using this formula we found the entropy. Once we found the entropy, we have to find these are 2 values we have obtained. We have to find the overall information gain for this attribute. We can find this information gain from this formula. We found the entropy of the nodes. This describes the entropy of the nodes. That entropy has to be subtracted from the original entropy. This original entropy is nothing but entropy of the target variable's entropy. See, this is our target variable. We found the entropy to be 0.918. From these attributes entropy is subtracted. So now we got the information gain for this particular single attribute. Now similarly we find information gain for the other attributes. So see, again this attribute has 3 categories: small, medium and large. And when the engine is small, 6 of them do not go fast, one car goes fast. And again we find the entropy for each of the category. From this category we have added them and we have subtracted from the original entropy. So we got again the gain for it. Similarly, other attributes we found, we got the information gain for each attribute. Finally, for this, see, we got the gain information of the engine, AC turbo, weight and fuel economy. Out of this, the information gain is more for the fuel economy. So we choose fuel economy as our first attribute for making our decision. This is how, as our first attribute to make our further decisions based on this information gain value. If we see this in fuel economy has 3 categories: good, average and bad. Out of this good, average and bad, once we look at the table, when fuel economy is good or average, all indicates that the car do not go fast. So all these models, with 5 of the models, the car says do not go fast. So this is when the fuel economy good or average, definitely the car will not be going fast. So we made our decision as no, the car will not be going fast. So we are left with only when fuel economy is bad. When we look at here, when fuel economy is bad, There are cases the car may go fast and some cases the car do not go fast. 10 rows which are bad category. From there we have to decide, we have to choose our next child node for this fuel economy to make further decisions. So now we left with engine, SC turbo, weight. We have to find the information gain to choose one of these attribute to make our decision. So again we calculate entropy for our target variable. Then we found the entropy in the similar fashion for the leftover attributes. So we got the information gain 0.213. Similarly for weight, this is our entropy, original entropy, subtracting this entropy. Similar way we found for other attribute. So finally we got the information gain for other engine attribute and SC turbo attribute and weight attribute. In here the information gain is more for the weight attribute, so we choose weight as our next decision node. First we choose fuel economy, instances of the fuel economy. It has made a decision of no, and we are left with 10. From this 10 we got our next attribute as weight. In this weight we have 2 lightweight cores, 3 average weight cores and 5 heavyweight cores. And all the average cases showing yes. So in this case we are choosing this weight decision to be yes, and we are left with car with lightweight cars and heavyweight cars. So if we choose the car with lightweight cars, again we have to choose next node. We are left with 2 nodes only, 2 attributes, engine and SC turbo. So again if you find the information gain, we will get SC turbo. See, if we choose SC turbo, when SC turbo is no, we are getting car is to be no. Similarly, when there is a car with SC turbo, then the car goes fast. See, this is how we decided. So in the lightweight case, when the car has an SC turbo, then the car goes fast. Yes. When the car do not have SC turbo, the car do not go fast. It got decided. And next case is car with heavyweight case. Now there are leftover where attributes are engine, SC turbo. So one of the attribute has to be chosen after this weight attribute. But thing is, if we carefully observe here, in this engine we are leftover categories are medium and large. Similarly for SC turbo, leftover categories are no and S. Now when engine is medium engine and there is no turbo, the car goes fast. Yes, it is saying that car is going fast. Similarly, again if you take another example here, when the engine is medium engine and SC turbo is, there is no SC turbo, the car is not going fast. And also you can see here large, when the engine is large, there is turbo, car is not going fast. Again when engine is large, the car is, there is no SC turbo, there is no turbo, again the car is not going fast. From this we can clearly say that the decision tree will stop here. We won't further proceed further. And if you see that last category will be most of the case it is showing no, so it will make it is most probable decision it will choose to be no. That's how a decision tree works with information gain. This example what we seen is an ID3 example. Here this type of model would not work well when there is an attribute with more number of categories. If there is an attribute with more number of categories. Now coming to the final other type of impurity measure is gain ratio. Like Gini, and the information gain ratio is another attribute to measure the impurity of the node. To find the gain ratio, we first find the gain split. This gain split can be found from the information gain. That's what we found, right? Gain split. So we'll find the gain split divided by the split info. Split info is nothing but, see, this is nothing but the, we'll find while we're doing a weighted average how we will calculate these values. So producting to the log. So by dividing this value we'll get this gain ratio. The main advantage of this gain ratio is they are capable of handling missing values, and also they can also handle if there are more number of categories within the attributes, unlike which is fails in the cache of information gain. This gain ratio can handle it. Gestation is in general more prone to the war fitting. To mitigate this issue, we use two types of prunings, like post pruning and pre pruning. Thank you. Now we will see implementation of this decision trees in Jupyter Notebook.